So, we will start with the basic introduction for tissue engineering today. So, we briefly looked at the course content. So, I also kind of said what tissue engineering was. Today, we will go into depths. So, we will have a few classes where we discuss introduction to tissue engineering. So, what is the motivation for tissue engineering? What do we really want to do? Tissues are actually lost and damaged every day, right. So, it could be due to injury, disease or congenital malformations and so on. So, due to different reasons tissue is usually damaged. So, but you want to restore these damaged tissues, right. So, you want, the dream is to restore it so that life can go on forever, especially for loved ones, and we want to make sure that tragedy never strikes us, right. So, that we do not have to go through the pains of whatever the process is. So, this idea would have is not new. It's obviously it should have come to a human being when the first death occurred or when the first lost limb was seen. So, why have we not been able to achieve it? Because we have always had dreams. We have, as humans, we have wanted to fly. We have been able to invent an airplane and so on. So, most of our dreams we have kind of achieved at least. So, whereas here, which is one of the most fundamental dreams, right. So, we want to basically create another life. So, why we have not been able to do it? The simple reason is the challenge is life. Life itself is very complicated and beautiful. See, we do not think about it. So, most of us here have a biology or a biotechnology background. So, we do know some of the things about how life starts, but we actually do not sit back and think about it. So, just think about this. So, what you have is what I have shown here is basically what I call the power of one cell. All organisms, whether it is a mosquito or a human being, start from one cell, right. So, this is very unique. The single cell basically divides and starts differentiating to form different tissues. So, it starts migrating and it has to differentiate to form various types of tissues. It could be a skin tissue or a bone tissue or a cartilage or a heart tissue and so on. So, all these migrations and differentiation have to happen over a period of time, and finally this eventually develops into the right organism. So, a human being or an elephant or a mosquito, all of these develop from this one cell within a very short period of time. So, if you were to take humans, it takes only 282 days for a cell to become a fully grown baby, and that is a very short period of time, considering our lifespans and the lifespan of the earth itself. It is actually a very small period, and within that time there is such regulated control which is phenomenal. Almost always we get proper development, right, and that requires so much control over how the cells migrate, how the cells actually divide, how the cells differentiate and so on. For us to first understand what is happening itself has been a challenge. We still do not fully understand what is happening and why it is actually happening the way it is happening. So, for us to first understand and then to actually recreate it is the challenge of tissue engineering. So, to create an entire human is completely out of question at this point, but to create tissues, can we understand enough to know that what is required for creating this tissue, and that itself is a big challenge. So, that is where the field is, and we are working on it. So, we need to understand some of the fundamentals, because see, tissue engineering when it started actually had a lot of promises which were made, because it was primarily just engineers who were starting it and with some doctors. So, probably we did not have enough of an understanding of the complexities associated with basic biology. So, there was actually one paper which promised to deliver a heart in a petri dish by the turn of the century, and this paper was published in 93 or something, 1993. So, within 7 years people were thinking they can create a heart in a tissue, because what they thought was you take the material, you put the cells, you will have the heart. It just turned out it was not that simple, and people are still struggling to get even a beating tissue. So, recently maybe about a year and a half back there was this huge rage, which was the videos were being forwarded where a small piece of tissue which was beating was actually created. So, it has taken us more than 25 years to create that small tissue, and valves are a whole another ball game. So, there are so many challenges which were not foreseen, and as we started doing more and more, people have started realizing there is a lot of challenges associated with this field, and people are trying to address them, and that is where we as researchers should contribute. Currently people do treat damaged tissues, right. So, there are different techniques you can use. So, graft implantation is basically the approach. So, there are different types of grafts you can have. You can have an autograft, which is basically from yourself. So, here the advantage is it will not get rejected because it is part of your body, it is not going to get rejected. But the problem is there is very limited availability. It is not easily accessible because you will have only limited tissue in your body. I cannot completely harvest a particular tissue, and if it is an organ, like for example, if you have diabetes and you want to replace your pancreas, then you do not have another pancreas, you cannot take it from your own body. So, you need to get it from an allograft, which is another person from the same species. So, here there is a risk of disease transmission, there is a higher availability, but there is always a risk of disease transmission and rejection. Even with transplants which have been very well established. So, what is the most common transplant that you can think of? Organ transplant? Liver, heart valves, kidneys. Kidney is probably the most common one. Liver is also done, but liver is a much more complicated procedure than kidney. So, kidney is probably something which is very commonly done, but heart valves, usually cadaver heart valves are also used, but people use from other animals as well. So, that would be a xenograft. So, where you take from pig or from cows and you take them for your xenografts. Yeah, that's as well, that's also a transplantation. So, if you are talking about an organ transplant like kidney, which has been well established, it has been done for almost half a century now. Even for that, people still have to take immunosuppressive drugs for their life. That puts them at a risk of getting infected at any point. So, it is a serious problem to even have one of the most well established surgeries. So, that is a problem with allograft, and xenograft, obviously it is going to, risks are going to be much higher compared to allograft, because you are now talking about a different animal altogether. So, your chances of disease transmission and immunological rejection are significantly higher. So, the last option is using synthetic materials. People use polymers, metals and so many other types of biomaterials, so that it can actually be used for implantation. So, this also has inflammatory responses, and there can be a vascular barrier. So, cells may not infiltrate. For example, if you are using a hip and joint replacement which is made of metals, cells are not going to infiltrate. It is not actually a biologically active tissue you have placed. What you have is just a mechanically supportive device which has been placed. So, that causes some discomfort. There can always be complications because of that. In some cases, like where you have plates and screws for broken bones, you might have to go back and remove them because there might be some immunological issues. So, these kinds of problems exist with the graft implantation, but that is not the only reason you want to do tissue engineering, because tissue engineered products can also have similar problems, right, because you are also going to use synthetic materials or materials which are not common in your body, and you are probably going to use cells which are not your own. So, tissue engineered products could also have the same kinds of problems. Then why do tissue engineering?
Maybe it's the best chance for us to mimic the living cell condition in the body.
Okay. So, probably you can get a closer tissue which is closest, but wouldn't an allograft be the closest? Like obviously an autograft would be the best, but autografts might not be available. So, if I can get it from another human being, that is God's creation, right?
Limited source.
Okay, limited source, yes. So, the major problem is this. This is the statistics from US. You can see how the trends have been when it comes to the number of transplants, number of donors and the number of people in the waiting list. The gray curve you see is the number of people on the waiting list, and the orange one is the transplants and blue is the donors. So, obviously the transplants are higher than the donors because a donor can actually donate more than one organ, right. So, this is the trend. And the gap seems widening, right, from 91 to 2017, the gap is much wider. And the problem is, this is for a developed nation like US, where you actually have 54% of the people registered for organ donation. So, we will start with history. So, this is something which you would see in any tissue engineering book, not exactly these images. What you would see is an image of chimera. So, this is to say that people have been dreaming of enhancing organs and enhancing tissues and so on. Okay. So, this is basically what people start with in a tissue engineering book. So, I always felt, okay, we should why start with a Greek mythology, why not our own mythologies, right. So, this is where we all this is something we have all seen, and I would also go to the other mythologies and show how similar our imaginations have been. But the cool thing is, people have actually dreamt of this, people have actually thought of xenografts, right. Lord Ganesha is a xenograph technically, right. So, why I said that disclaimer was, again, I am not saying a xenograft was actually performed. It is something which people wanted, people have been thinking about, right. This is basically what people are trying to do. So, the images I have are Lord Ganesha and Lord Narasimha. So, Narasimha was just an avatar who came down with the head of a lion and so on. Ganesha was proper xenograph, where the head was chopped off and you placed an elephant's head. So, the other two things which you see, the Kamadhenu and Yali, are more of mythological creatures which are basically designed based on what we think is cool, what features you would like to have, right. So, why I said there is similarity is, look at the other cultures. The one you see here, which is Al Burak. So, this is a mythological creature by Islam, and you see that it is a white animal, half mule, half donkey, with wings on its sides and a woman's head and tail of a peacock. It looks eerily similar to what you see as Kamadhenu, right. So, Kamadhenu, instead of a mule, they imagined it to be a cow, cow being the sacred animal for Hindu mythology, and a woman's head with on the feathers and peacock's tail and so on. So, you see that people were thinking along the same lines, and chimera is actually very similar to what you would see as Yali. Yali is a Tamil mythological creature. So, if you go to any of the temples, the older temples in Tamil Nadu, you would actually be able to see Yali. So, these are there on all the statues. So, chimera is something similar. Chimera is actually a Greek mythological creature, which is a lion with the head of a goat from its back and a tail with a snake's head. And actually Yali is also that. Yali has the lion head and the tail is actually a snake, but you also have teeth which is from elephants. So, it's like wanted to look at all the cool features, put them together. So, Tarask is a Christian mythological creature, and it's a dragon with a lion's head and a bear's legs, ox-like body covered in turtle shell and so on. So, why I show this is what people imagine. People thought of doing this because people were looking to enhance tissues, people were looking to add additional features to what would be a regular animal. So, leaving beside mythological history, if we were to go into the real history, there are folklores of nose transplants which happened in 1000 BC. So, 3000 years back, people had lost noses because of because they were in battles and they got syphilis. And during if syphilis proceeds to extreme cases, you actually lose your extremities and or some nose and ears and things like that. So, losing a nose was really a problem because you looked ugly when you did that, right. So, people wanted to replace that and they tried to put transplants. And the official recorded plastic surgery was done here in India, and this was done 800 BC by Sushruta, who is considered as the father of surgery. So, here he tried to use skin grafts to create reconstructive surgery, which is what is being done even now when you actually try to do skin grafts. So, that is what an autograft would be. An autograft, when somebody goes through a burn injury, you actually take your own skin and try to apply it. Can you think of another autograft other than skin?
Sometimes your hands just happen this way.
Okay.
Give you bypass surgery.
Bypass surgeries. So bypass surgeries usually use your own vein, and that's would be an autograft too. And there is actually a long gap between 800 BC and 16th century. There is not much of a record of what has happened between that time, but in the 16th century people tried to build nose replacements using the forearm flaps, and transplantation of teeth, cornea, skin were all performed in the 1700s and 1800s. And in 1933 this is what people were looking at immune rejection, and they were trying to understand how you can protect some implant from an immune system. So what they did was they took tumor cells and wrapped it using a polymer and implanted it in a pig to show that this polymer can actually prevent immune rejection. And kidney transplant was first done unsuccessfully in 1936, and liver and bone marrow transplants were done in 1960s and so on. Lung transplant was done in 1963, heart transplant in 67. Okay, so a modern era of tissue engineering itself started sometime in the 1980s, and this is a very recent development. So this is a modern day chimera. It was actually done by Charles Vacanti, and what he did was he took a polymer scaffold and seeded it with cow knee chondrocytes. Chondrocytes are basically cells which are there in cartilage, and put that in a skid mice. This is a immune deficient mice, and showed that you can actually create a ear. So obviously this is not a functional ear. This would only be for plastic surgery, just to for the aesthetic reasons. It cannot really help you in listening or anything, but it was a start, and this was done in 1997. There have been many other recent studies. So these you might have seen. So I don't know if anybody has seen this image where you see the forehead having a nose. So this was on the first page of Hindu, maybe a couple of years back. So this was done in China. So this guy met with an accident and lost his nose. So the Chinese doctors decided to put a polymer scaffold on his forehead and let the cells seed themselves and create a new nose. And this was eventually transplanted to his nose, and I'm hoping he's healthy. But the other one you see is a ear on a forearm. So this has been done multiple times now. So recently it was done for a US Army officer, I don't remember her name. So but anyways, so she had lost her ear in combat, and they grew a ear on her forearm and replaced it. Again, it's only for aesthetic reasons. I don't think it provides the functionality, but it has been reasonably successful. And there was actually an article which basically said forearm is the best place to grow a ear or something like that. So people have been quite successful in doing that. So these are the more recent studies, probably happened within the last 5 years or so. So what is tissue engineering? So this is the definition of tissue engineering. So the term itself was defined by the paper in a paper published in Science 1993. So this was written by Robert Langer and Joseph Vacanti. Joseph Vacanti is different from the Charles Vacanti. They were not related. So Joseph Vacanti is a medical doctor, and Robert Langer is a chemical engineer. So these two people came together to write a paper. So this was a review article which was published in 1993. So they defined tissue engineering as an interdisciplinary field that applies the principles of engineering and life sciences towards the development of biological tissues that restore, maintain or improve tissue function or a whole organ. Okay. So this is what the definition itself is. So what you see here is basically an image from Wikipedia. So there is a damaged tissue. You take some cells out of the person with the damaged tissue. You then culture the cells, you get enough of the cells, you put them along with the scaffold and give them the signals. So with this you now should have a fully functional tissue which should replace the damaged tissue, and the person is okay after that. So that is what this image represents, and this is exactly what you try to do. The challenge is with identifying what type of cells, how to isolate the cells, how to culture the cells, how to design scaffolds, how to make sure the cells attach to the scaffolds, how to make sure the scaffolds do not get rejected, what kind of signals should be provided, and what time it should be provided, at what rate it should be provided, whether it should be provided in sequences or not, and what other biophysical cues are required, and then with all that hopefully it will have the function to the end. Okay. So, that is the idea. So, those are the challenges in the steps which have been shown here. So, the first term in this definition was interdisciplinary field, right. So, it is also one of the hot tags to have, but this is truly an interdisciplinary field, and it was defined as an interdisciplinary field 25 years back. It is not because we want to get funding, so we call it interdisciplinary, right. So, why do I say it is interdisciplinary? What disciplines do we want? What expertise do we want?
Life sciences, material sciences.
Okay, life sciences, material sciences,
Doctors, medicine experts.
medicine. Okay. What else? Okay, mechanical engineers. You also have to justify why you are saying all these, but we will get to that.
Chemistry.
Chemistry, okay.
Does developmental biology?
Okay, so developmental biology,
Also maybe synthetic biology.
synthetic biology, okay. Anything else that you can think of?
Aesthetic biology.
What?
Aesthetic.
Aesthetic biology.
Like aesthetic experts.
Okay, so aesthetics. So are you from engineering design?
Someone who knows it, like from the arts side is for ethics.
Ethics. From what side?
The arts, humanities.
Oh, humanities side, okay. Humanities is different from arts.
We did the arts degree.
Chemical engineer.
Okay. So thanks. Otherwise I would be wasting my time here. So.
Instrumentation.
Okay, so okay, let's first justify why we have all this. So life sciences, it's quite obvious we are working with living systems, so we should have life sciences. So why specifically developmental biology?
Because you can take. So if you want to regrow some kind of cells, you can make the cells into tissues by using stem cells. So I have to read up on that. It's just
Okay.
something
So
to talk.
developmental biology is the domain which actually says how tissues are actually developing. So if you have an understanding of that, hopefully you can recreate it. Okay, so good. What about material sciences? Why do you want material sciences?
Biocompatible main thing. The materials whatever we are taking, it should be biocompatible.
So why do we even need materials?
Of course we are dealing with polymers. Because many of the things we should not do the
Why should we use polymers? So why should we even use materials? Why not just use cells? Mammalian cells are adherent cells. They need a substrate to which they can adhere to. They cannot just grow in suspension like bacterial cells. Okay, so that's why we need materials. Okay, now continue. What do you want? So why do you need a material scientist?
So there are some of the materials which had to be biocompatible in nature. So
Okay.
material science one people can know what other materials can be actually biocompatible in nature.
Okay, so they can design the materials which would be compatible and also functional. So it's not just compatibility. Compatibility can just mean that it's not toxic, but it could also require some functionality with it. Okay, why do we need medical experts? To execute it. Okay, so that's the
Clinical trials.
okay. So you're reducing them to technicians. They are more useful than that. Sorry.
The end goal is to put it in a human body.
Okay.
And they have an understanding of human.
Okay, getting information about the anatomy and physiology, sure.
And they'll be required if we're building in the order of anything, surgery will be required to.
Okay, so finally for implanting it, you need them as surgeons. Okay. What else? They are the ones who can actually identify the problem. Okay. So it starts from them. So see, many a times what happens is we as engineers don't really know the need. So some of the needs are we just take it for granted. We don't think it's a big need, but turns out they are actually big needs. So see, recently I was talking to a doctor who was saying, so he's a dentist actually. So but he was saying there is a serious problem in dental issues where people undergo cancer, bone cancer, and you need to have some small diameter vascular grafts which have to be placed, and engineering those have been a big challenge, and he was looking to understand what would be the issues there. So I would not have thought of vascular grafts as an application for dental procedures, and especially in cancer patients. I would have thought of it for an application in cardiovascular procedures. So those kinds of things we might not know, because those are the guys who are actually doing it every day, right. So it's important to have a conversation with them. So there was another doctor who gave a talk here some time back. So he actually was saying the heart valve. So I don't know if you has anybody seen a heart valve? Not a real one, like the mechanical heart valves. Have you seen a photograph or anything? Okay, so the mechanical heart valve basically looks something like, it looks like a regular heart valve with a flap, and there is a cylindrical metal which is covered by a cloth. So this cloth is usually present so that it can be sutured to the patient, and it will hold it in place. So the metal which comes in contact with the blood, all that the flaps which come in contact with the blood, all that are quite biocompatible, and people try to coat it with different materials to ensure that it is compatible. But this cloth was something which was causing a problem. But without a cloth they could not implant it, otherwise it will get displaced. But all they had to do was, finally these guys were sitting together and with a group of engineers, and they figured, okay, just remove the cloth and put holes in the cylinder, and that holds it in place, and it removes a major limitation which has been causing clogs and clots in the implant. So it's a very simple solution which was proposed by an engineer, but nobody would have guessed that there was a problem there unless a doctor came to them and said that, hey, this is a problem. Okay. So doctors are very useful in identifying the problem. Okay. Okay. So why mechanical engineers?
If you are designing a blood vessels and the flow dynamics of the blood and how it would impact the, like, you have to design a model for it so that we can properly test it before we implant it. Or if you are modeling anything for bones, so will the material which we are using be able to take on the stress which would be applied on it once implanted, or any body motion that can the implant actually will be able to perform all the different ways in which we can move.
So the mechanical properties and the mechanical stresses which our tissues go through have to be understood, and you need some expertise in that. And there is also mechanical signals which can actually regulate how the cells migrate and cells differentiate. So that also needs to be looked at. So there are different aspects where a mechanical engineer could contribute. See, we are all standing upright, right? It's actually the worst thing to do. It's not good for your knees, it's not good for your joints. You're putting all your body weight on your ankles, which are probably crying for you to sit down. You're much better off when you walk in force, because your stress is now, your body weight is distributed much better. So you're obviously going through something which is, the stresses which you're going through are severe, and this needs to be understood, and this might have to be emulated for making it into a viable tissue. Okay, so mechanical engineers can help you there. So chemistry, why chemistry?
I don't know whether it's reality or not, but there are prosthetic arms and all which can detect whatever, if the person thinks in a particular way, that is to flex the fingers actually flex. So can chemical signals be used in that way?
I don't know exactly what is being used to get that. I know I have also seen those videos and seen lectures where that is possible, but I don't think it is chemistry. It is more with electrical engineering, because it's not that it is being implanted in their body for them to actually have a chemical connection. It's mostly just put on top of an amputated arm or something. So, I would think it's more about the electrical signals rather than the chemistry. Yeah. So, I do not have enough understanding of the electrical engineering aspect to actually comment on that, but that brings to an aspect where electrical engineers can also be useful because you have nerves and heart which have electrical signals, right, and muscles. So, all these things have electrical signals which are being processed. So, chemists can actually be very useful because chemists are the ones who can actually tell you how to design materials. Okay. So, that is one major step where they can help you, and they can help in how to actually functionalize materials. So, if you are going to know what you need to know what chemistry is required for actually functionalizing a material and so on. And aesthetics, yeah, that is quite obvious, and humanities, as you said, for ethics it could be useful to have a humanities person, and but probably I would like to bring them in to the, at the end of the project, so that they do not kill the project on day one. So, chemical engineers, chemical engineers are basically working in this domain for a long time because they have the expertise with respect to polymer engineering and also with respect to transport, fluid mechanics. So, the chemical engineers know a little bit of everything. So, like when I joined chemical engineering, one of my professors used to say this: chemical engineers can speak chemistry to engineers and engineering to chemists, so that you can basically show off as if you know something even when you do not, right. So, you can actually fool people that way. So, you are actually know a little bit of everything, so people can actually contribute. So, at least I hope I can. So, we will go into the, so some of what I have you have already mentioned. So, we will see what else I have. Basic biology. So, in that you had mentioned developmental biology. You also would like to have cell biology and molecular biology, because you are ultimately going to know want to know how the cells are to be cultured and if they have to be engineered in some way, and immunology, because ultimately you want to know what the rejection process would be and how you can prevent that. Engineering, I have just clubbed all engineerings together and put it as transport properties, mechanics, 3D, 2D, 3D tissue growth, reactors, and even storage and shipping. So, where an industrial engineer would be useful, right. So, chemistry and materials people I have clubbed together because they kind of works hand in hand, because you want to design biomaterials, look at compositions and structures. So, how the scaffolds can be, biocompatibility, surface functionalization and characterizations. See, anytime you prepare a material, you have to characterize it thoroughly. To fully characterize it, you need to have enough expertise in chemistry. Without that, you would not be able to understand what you see for an FTIR or an XPS and so on. So, then I would have to spend a little more time on the characterization aspects. So, it is crucial to understand how you can characterize biomaterials. So, physics people are also useful because they also have understandings of the fluid mechanics, mechanical and electrical effects on cell differentiation, electrical properties of tissues and so on. So, I am just clubbing them all together as physicists. So, in addition, medicine, so for understanding the need and the solution, surgery, clinical trials, patient care after surgeries and so on, you need medical professionals. Last but not least is informatics. For any kind of work which happens today, you do need informatics people. It could be for sequencing, image analysis, quantitative cell and tissue analysis, modeling, or even clinical informatics and so on. Okay. So, for different reasons you need different people, and all of these people have to come together to actually make it into a viable industry. So, this kind of a cross pollination is required for the field to emerge to be a more successful thing, and that actually is one of the major challenges in the field. So, because it is very difficult for people to communicate when they do not speak the same language, and where people with different kinds of training usually do not speak the same language. So, you go and talk to a basic biologist, the way they think would be very different from the way an engineer would think, and even a traditional research based engineer, you go and talk to an industry based engineer, they are going to think very differently. So, I like to narrate this story. I don't know if you guys have already listened to the story before, but you might have to listen to it again. So, when I was a PhD student, my the head of the department at that time, he had his PhD in transport phenomena and like related to transport phenomena, and so he had done downstream drying, all those things. So, he went into an industry job in this. So, this was a polymer wire manufacturing company where he was working. So, they wanted to actually have a system where there was an extrusion of this polymer wire and it was being spun on a spindle in an X shaped fashion. So, it was just going this way. Okay. So, what happened was this was a wet polymer wire which was coming out, and as it was being spun out, there was like some difference in the thickness depending on which part of the spindle it was being assigned to, right. So, there was like some places were thicker, some places were thinner because there was a little bit of stress because of this pulling. So, his first boss basically asked him to solve this problem. So, figure out what the problem is and try to solve it. So, he was a fresh PhD guy, fresh out of his PhD. So, he looked at the problem, started looking at basic transport phenomena, wrote down the Navier-Stokes equation and tried to solve it to come up with what, did all that. So, came up with, and this was, it must have been in the 60s or 70s. So, there were no computers or anything. So, he spent about 25 days trying to solve the problem, and then went and took a nice engineering report to the management boss. Management boss then said, oh okay, good, no, you know how to implement it, let us call the worker and let us implement it. Like the worker was called and he was like, sir, that problem was solved already. Why, what did you do? We just put a fan there. So, it was wet, that was the problem. So, you just put a fan there and it was dry, and it did not. So, it is about how you think, right. So, you would not think of that solution because you have come to a point where that solution seems stupid to you, but that works, and that is all you need. You need a solution that would work, right. So, why is it, this is an extreme example which I am giving, but between an engineer and a basic biologist, you would always find this difference. A biologist would want to know why it is happening. To me, I do not care, as long as it happens, it happens. It's good to know why it happens, but more importantly the outcome has to be there. So, the difference in this approach causes a lot of problems when you are actually trying to collaborate and trying to establish things. So, we already defined the ultimate goal is to restore tissues. How do you restore tissues? So, I like to call these as the 3 R's of tissue restoration, and this is tissue regeneration, repair and replace. Regeneration is basically where you try to replace lost tissue itself and initiate the regeneration where you normally do not observe it. You try to provide some support so that it can regenerate. You can have tissue repair where you enhance the rate of repair where it is seen sometimes. You can also deliver molecules or drugs that can aid in repairing the tissues. And the last one is to replace. So, when all else fails, what you do is you replace the tissue, you take the tissue out and put a new substitute there. Hopefully, that will take care of the function which the actual tissue was supposed to do. So, this is the way tissues are supposed to be restored. For accomplishing this, there is something called the tissue engineering triad. So, this is an updated tissue engineering triad which was published in 2016 again by Langer. So, this was published in Nature Protocols which is so this talks about, so the tissue engineering triad itself basically talks about 3 things. You have cells, materials and signals. So, those are the 3 things here, and they have also put what are the new cool aspects which have actually come out. So, you have for the cells there are new cell sources and there are new technologies for engineering the cells. So, you have things like CRISPR-Cas which can actually be used for engineering the cells. Recently you have the development of iPSCs. So, what are iPSCs?
Induced pluripotent stem cells.
So, induced pluripotent stem cells, what are they?
These are
We take differentiated cells and we reverse them back to make them pluripotent.
So, somatic cells are reversed to become pluripotent by using 4 transcription factors. So, that is what an iPSC is. So, that those kinds of cells have made sure that you can actually have personalized medicine now, right. So, all I would need is some blood tissues cells from the patient, and I can make it into a pluripotent cell and then differentiate it into the type of cell I want. So, that would give a personalized medicine. So, you also have signals. So, now people have understood novel chemistries, people are looking at different growth factors, people have a better understanding of the signaling molecules which can be used. People also now understand that mechanical features and physical and electrical cues can actually help in cell differentiation. So, because of all these things, we have a much better understanding of how to engineer materials for providing the desired signals. The last but not least, we also have very cool technologies for creating tissue architecture, starting from self assembly to decellularized organs to 3D printing, right. So, there are just too many technologies which have come up in the last 10 years, which have which are now giving a lot more promise towards the field of tissue engineering evolving into something which is fully successful. Thank you.